here's our first topic for Unit 4. This unit is actually divided up into two sort of different big topics. One is just on solutions, and then the other part of the unit is on acids and bases, which are specific kinds of solutions. So we're going to start off with a bunch of definitions for you to fill in your notes. So, whoops, let's go back. So the first definition here, first couple of definitions, you've probably seen before, homogeneous and heterogeneous. So a homogeneous mixture is a uniform mixture of only one phase. So uniform is the key thing there. Basically, you can only see one phase. So if I look at salt water or if I look at Kool-Aid, I can't see all the different particles that make up those mixtures. It kind of all looks like one. A heterogeneous mixture, on the other hand, is a mixture that consists of physically distinct parts, so I can actually see the different parts. So for example, if I see smoke in the air, I can distinguish where the smoke is versus the clean air. Sugar and salt mixing together, if I look closely under a magnifying glass, I can actually see the different crystals that are the salt and the sugar. All right, and then we got three more definitions here. So, a solution is a homogeneous mixture of substances that are composed of at least one solute and one solvent. The solute is the substance that is dissolved into a solvent, and then the solvent is the medium in which a solute is dissolved. And it's often the liquid component of a solution, but it doesn't always have to be. The most common one we use is water. So those are your definitions. If you need to pause the video to finish copying down all of these, you can do so now because I'm going to go on to the next topic. So a solution does not always consist of a solid dissolved in liquid. That's sort of the most common one, but I'm going to give you some examples of solutions that are not a solid dissolved in a liquid. So for example, if we have a gas and we dissolve another gas into that, that could also be a solution. An example is oxygen dissolved in the air. So it would be a homogeneous solution because you can't see the different parts of the oxygen, how it's different than the rest of the air. So it would be a homogeneous solution, but because you have something dissolved in something else, it's still considered a solution. You could also dissolve a gas in a liquid, and you guys have probably already seen these before. Carbon dioxide in soda or in pop. Okay, those bubbles in your pop, that's actually carbon dioxide, which is a gas, and it's dissolved in the liquid. So there's another example of a different kind of solution. Can also have another example of a gas dissolved in a liquid. Oxygen in water. So in order for fish and plants and all those things to survive underwater, a lot of them need oxygen because they can't make their own oxygen. And where does that oxygen come from? Well, it comes from the water, and it's actually dissolved in the water. So that's another example. Here's an example of a liquid dissolved in a liquid, is alcohol dissolved in water. So we often dilute alcohol to various concentrations to make it more safe for us to handle. So that's an example of a solution that's made up of a liquid and a liquid. And last one, something that's a solution that's made up of a solid and a solid. This one's a little bit tricky, but a metal alloy. So things like stainless steel that are made up of, or brass, and they're made up of basically more than one type of metal. That would be an example of a solution. All right, here are three more definitions for you, and I have a picture. So if you want to just sit and listen to my definitions and my explanation first, and then you can pause the video and copy down your definitions, that's up to you. So an aqueous solution we've already looked at before. They basically have water as the solvent, okay? And we've got anything that's aqueous, oh my. Anytime we've got anything that's aqueous, we denote that with AQ. And my smartboard is not working today. AQ. Great. Okay, so let's see if we can keep going. Electrolytes are substances which, when dissolved in water, produce a solution that conducts an electric current. Okay, so I can actually show you an example of this in class. A really good example is salt water. Okay, so that's the example that I sort of gave you here. Wow, my smartboard is not looking so pretty today. Non-electrolytes are solutions of these substances that will not conduct electricity, for example, sugar and water. So if you take a look at this picture right here in a little bit more detail, kind of try to make it a bit bigger. Oh, no, it doesn't want to get bigger. In the first example of the electrolyte solution, so this one right here, sorry about my messy marker, you can see that the sodium chloride ions are dissolved in water, and when they're dissolved in water, they're actually separate. So I've got negative ions here and positive ions there. Wow, this is terrible. And when they are dissolved in water, they're separate. Because they're separate, now what can happen is if I try to put an electric charge through the solution, the electrons can actually move through the water because there are charges that will repel it and attract them. So that allows me to move electricity through it, and therefore I have an electrolyte. The non-electrolyte solution, so for example, sugar and water, when sugar dissolves in water, it still stays in a big, huge molecule. So you can see there are big molecules there for that are the sugar. So I'm not separating out any ions because there are no ions in a sugar molecule. It's a covalent compound. So because I have no ions, I've got no place for these electrons to move through the solution, and therefore it will not conduct electricity. All right, so why are some things soluble and some not? A solute's ability to dissolve in a solvent is always dependent on the potential intermolecular forces, so your dipole-dipole forces, your London dispersion forces, or your hydrogen bonds that can occur between them. So let's have a look here. Here's our rule of thumb. Like dissolves like. And I think we've talked about this earlier on in the course. So if something is polar, it will dissolve something else that is polar. And if something is nonpolar, it will dissolve in something that is also nonpolar. But if you try and mix the two together, so if I try to mix a polar solvent, such as water, with a nonpolar solvent, such as oil, we're not going to actually see them mix. So here's a funny comment that I like to show in class sometimes. Help, help, I'm dissolving. But bears are insoluble. That's easy for you to say. You're not polar. Ha ha. All right, so have a look at these. I was actually going to put the answers up on the board, but my smartboard's not working, so I'm just going to talk it through, and we can go through them in class if we need to. So example, is it soluble? Why or why not? So if we take ammonia and water and try to dissolve them together, will they mix or not? Are they going to be soluble or not? In this case, so for example A, we know that water is a polar. Oh my goodness, that's terrible. So water is going to be polar, and ammonia is also polar, okay? Both of these can also make hydrogen bonds. I think what I'm going to do is just type, okay? So these are both polar molecules, and they can actually both make hydrogen bonds. So are they soluble? Yes, they definitely are. If we look at propanone and chloromethane, option B, again, what's going to happen here? If we look at propanone, that's the first compound there. It's got this C double bond O group in the middle, which is slightly polar, okay? So the propanone is polar because of that middle carbon and oxygen bond. The chloromethane is also polar. This chlorine is very much more electronegative than the carbon, so it'll pull all those electrons around it, making this area of the molecule partially negative. So again, in this case, they are both polar. Okay, oops, both polar. Now, they don't make any hydrogen bonds, but that doesn't mean that they're not polar molecules. So if they're both polar, that means they're both alike, which means, again, yes, they will be soluble in each other. Now let's look at option C. Let's scroll down a little bit here so you guys can see the last two. So if you guys you don't need to write down all the structures. I would never ask you to draw out hexane and figure out if it's polar or not. But if I give you the structures like this, you should be able to figure it out. So in this case, for water and hexane, water we know is polar, right? So water is polar and can also form hydrogen bonds. But if we look at hexane, hexane is not a polar molecule. There is no place for hexane to get more partial charges. So even though there is a difference in electronegativity between each one of those carbons and hydrogens, the electronegativity is A, not that strong, and therefore only LDFs exist. in hexane. So that means it is nonpolar. Nonpolar. Okay, so the answer for will they be soluble together? No, they will not be soluble because you've got a polar water molecule and a nonpolar hexane molecule, so they will not mix together. Last one, carbon tetrachloride and hexane. Again, in this case, hexane we already know is nonpolar. We kind of looked at that and looked at the electronegativity differences in the last question. But if you look at carbon tetrachloride, again, carbon and chlorine, there is a difference in electronegativity there. Chlorine is more electronegative and will hog those electrons more. But even though all those chlorines are hogging the electrons, there's no place for me to get a partially positive and a partially negative charge. So carbon tetrachloride, basically all of those dipoles here end up canceling each other out. And in this case, they both end up being nonpolar. I'll move this over, please. So they're both are nonpolar and they contain only LDFs, which are London dispersion forces. So if they're both nonpolar, they will be soluble in each other. Yes, because like dissolves like. So if I have two nonpolars, they will both dissolve in each other. All right. Last little bit of this video. Water is known as the universal solvent, and there's a bunch of reasons for this. First reason is your dipole-dipole forces and your hydrogen bonding occur in water. So it's able to dissolve a number of solutes. The other thing that's really awesome about water is that it's a really, really small molecule. So it can kind of get into nooks and crannies and help to dissolve a lot of different solutes. So remember again, when we looked at aqueous solutions, we can write aqueous solutions like this, okay, with the little AQ as a subscript, or we can write it like this, which basically means it's dissolved into its ions. So when something dissolves in water, it actually does break up into its ions, just like NaCl does in this example. So remember that, and have a look over here. It says here, ionic compounds will dissolve in polar solvents, especially in water, since they're able to form ion-dipole interactions. So ions will dissociate and are surrounded by water molecules. So this is an example of why NaCl can dissolve in H2O. So if you look at your sodium ion over here, oh, my smartboard seems to be working again. You can see that the partial negative charges on all of your oxygens are attracted to that positive sodium ion. If we look over at the chlorine is negatively charged, and so all of these positive H's are going to be attracted to that. So because these water molecules can surround these ions, it allows the ions to dissolve in water. If this doesn't happen, if we don't have the positive and the negative charges for the water molecules to surround, then that's how something would perhaps not dissolve in water. So that's why a lot of ionic compounds will dissolve in water. All right, I have this video to show you at the start. If you want to copy this link, you can watch it on your own, but I'm going to show it in our next class.